So here we want to do two select problems. The first problem is number 33, part B in chapter 23. So here we have a diverging lens, and we're told the focal length of the diverging lens is -4 centimeters, and we're told the object distance is 8 centimeters. So I'm going to go ahead and solve the numerical part first. So I have 1 over O plus 1 over I is 1 over F. So 1 over 8 plus 1 over I is equal to 1 over -4, because I have a diverging lens and my focal length is negative. And so 1 over I is equal to -1 over 4 minus 1 over 8, which is -3 over 8. And so if I flip it over, you got to remember to flip it over, you get I is -2.66 centimeters. And then the magnification is minus I over O. So the magnification is -2.66 divided by 8. And so the magnification here is going to be on the order of, let's see here, that's on the order of something like roughly a third, and it's positive. So because from the mathematics, because I is negative, we're in a virtual image where we have to trace the rays back. Because the magnification is positive, the image is going to be upright. And because the absolute value of the magnification is less than 1, we know that the image is going to be smaller. So we already know what we should see when we go and try to draw the pictures. So, yeah, I believe I'll have some room here to do this. So here is my lens, and I need to count out 8 units. 1, 2, 3, 4, 5, 6, 7, 8. So here's one. Oh, I'm sorry. The 8 units is where I'm putting my object. So I'll go ahead and make my object roughly 3 units tall. So here's one of the focal points. The focal points are at 4 units. So there are my 2 focal points. So the first ray is a ray that comes in parallel and exits for a diverging lens as if it came through the focal point. And so my first ray is going to come in parallel, and it's going to exit from the focal point on the left. So I'm going to draw a line. I'm going to connect my ruler to the focal point on the left and my point here. I'm going to draw a line that goes off this way. So that's what the ray does. And I know I'm going to need to trace the outgoing ray backwards. So if I trace the outgoing ray backwards, that would be like that. So that outgoing ray is coming from the focal point, and I see that it is coming backwards in that fashion. Okay, second ray, the third ray is the second most easy to draw. The third ray is actually the ray that goes through the center of any lens is the easiest to draw. So there's my ray that goes through the center. And of course, if I were to trace that ray back, we would see that the trace back is along itself. And we already see that the trace backs of these two are intersecting at this little dot right here. That little dot, I'll make a little red dot right there. That little red dot right there is where they're tracing back. And I can see that that is 2 2/3, right? So my image location, if I count it back, is 2 2/3. The third ray that I want to draw should point towards the focal point on the right. So I have placed my ruler at the tip of my object and the focal point on the right. I draw that ray up. I get to hold the ruler really still. I'm drawing that ray until I hit the lens, and then I draw a ray that comes out parallel from there. A little tricky to do with an iPad. So I'm going to draw a ray that comes out parallel from there, and if I trace that ray back, it also lines up right there. So we see that my object is here, and my object has the correct properties. It is upright. It is at 2.66 centimeters behind the lens. So again, the eyeball is kind of on this side, so anything on the same side as the object is behind the lens, so that's why the image distance was negative. And the height is roughly 1/3 of the initial starting height. And so we have completed the mathematics and the ray drawing of problem number 33 in parts B and C. The first part with the converging lens was a little bit on the easier side. I'd also like to, on the same problem or the same video, do chapter 24, number 3. This case, we're told that we have a wavelength of 440 nanometers. So that's 440 times 10 to the minus 9, because nano means 10 to the minus 9. It's falling on double slits whose spacing is 0.3 millimeters. So that's 0.3 times 10 to the minus 3 meters. And we're asked to find the angle and to the third bright spot on a screen that's 3 meters away, and also the distance to that screen. Now, I can't draw that to scale because you wouldn't be able to see the slit separation. So I'm assuming that this distance here is 3 meters, and I have blue light coming in, and the blue light is going to make an interference pattern on the screen. So what I'll see on the screen are blue dots, and the m equals 3 means this one here. So the angle I'm looking for is that angle there, and ultimately I want to find this distance y, which is in this orientation here. So the formula here is the formula here is d sine theta is m lambda, or the sine of theta is m lambda over d. Since I want the third bright spot, that means that m is 3. The wavelength is 440 times 10 to the minus 9. The distance is 0.3 times 10 to the minus 3. And when I solve for that, I get that the angle was 0.25 degrees. And then if I use some trigonometry, y over 3 would be the tangent of that angle. And I can solve for the distance y, which is this distance here along the screen. And that turns out to be 1.3 centimeters. So that's my angle and my distance using the idea of double slit interference.